now that we have solved parts A and B in our problem, we are ready to move on to part C. And in part C, we are asked to determine an appropriate domain and range for the function found in part B. Now, what was the function that we found in part B? Well, the function that we found in part B was this function a of x, representing the amount of area remaining, or amount of material remaining after we remove a semicircular piece, and that was a of x equals to 100 minus pi x squared over 2. Okay, so this was the function that we found in part B. Be sure to state your final answer using proper mathematical notation. Okay, so we're going to find the domain and range in the context of this problem. Okay, let's think back to our problem. And to figure out what we're going to write for the domain, we have to think about what are the inputs that this function is taking on. Okay, so in this particular case, the input for a function is this x value. And what does x represent? Well, x represents the radius of the semicircle. Okay, so what are some appropriate x values that we could have? What are some appropriate radiuses or radius for a semicircular piece? Well, let's go ahead and draw this image here. Now, what will be the smallest radius that I could possibly have? Well, the smallest radius that I could possibly have will be when I remove no circular piece. When I just have my entire square piece and I don't remove any semicircular piece. So what will be the radius at that particular case? Well, it will be 0. I'm not removing any semicircular piece, therefore I have no radius. Okay? Let's think back to the other extreme. What is the largest semicircular piece that I could have? Well, the largest semicircular piece that I could remove will be a semicircular piece that looks like this, where I have a diameter that runs along the entire length of one of the sides, and in which case, since the length of the side is 10, the radius has to be 5. So that tells me that I cannot remove a piece larger that has a radius larger than 5. Therefore, my domain has to be values of x, or radius, between 0, when I have removed no semicircular piece, to the largest semicircular piece that I could actually remove, which is one of a radius of 5. Okay, so that's the domain of this function. Likewise, let's look at the range. Now, for the range, we are looking for the set of outputs that we could come up with in our problem. Okay, now, since the output represents the amount of material left once we remove a semicircular piece, we have to think about these two cases again. I think the both extremes are a good starting point. So if I don't remove any semicircular piece, that will be the case where I have a radius of 0, like we saw before. I have removed no semicircular piece. How much material do I have left? Well, actually I have all the material left, right? So I have 100 meter squares of materials left. Okay, so that's going to serve as the largest output that I could possibly have, and that comes into play when I remove no semicircular piece, or I have a radius of 0. Okay. Likewise, let me just erase this. Oops. Let me just erase this right here. Once I remove the largest semicircular piece that I can, okay, so let's say I have a semicircular piece like this. I've removed that amount of material from my box or my square. How much material do I have left? Well, will have this amount of material, right? And in order for us to calculate that, we are going to find what is A of 5. Okay, so that comes into play when I have a radius of 5. How much material do I have left? Well, if I substitute 5 for x, I get 100 minus pi times 5 squared over 2. And if you take a second and you put that into your calculator, you will see that that is equals to 60.730. So that is actually meter square. That is the smallest amount of material that I could possibly have, and that comes in play once I remove the largest piece of material that I could possibly remove, or the largest semicircular piece. Yeah, so I put it here, 60.730. So those are our domain and range, domain of from 0 to 5 using proper mathematical notation, interval notation, and range from 60.730 to 100, including both endpoints. Okay, so now we are ready to move on to part D, which says, for x greater than 0, the function a of x can be inverted. Find an algebraic representation for a inverse of x. Okay, to find this one, I'm going to begin by rewriting my function a of x, which is 100 minus pi x squared over 2. And we discussed in class that to find the inverse function, we are just going to interchange the roles between the output and the input. Okay, in other words, we're going to replace x and y. Now, I don't have a y here, but this is my output function, a of x, so I'm going to name that y and rewrite the function, y equals 100 minus pi x squared over 2. So now, what I'm going to do is everywhere that I had an x, that's going to change into y. Everywhere I had a y, that's going to change into x. So x equals to 100 minus pi. There's an x squared, so that's going to be changed for y squared over 2. Now, our goal is to solve for y, is to isolate y. So I'm going to be using some inverse operations to isolate y. Okay, so I'm going to start by moving the 100, so subtracting 100 from both sides would allow me to cancel this 100, and I'm going to shift over here because I need a little bit more space, and I will get x minus 100 equals to negative pi y squared over 2. Okay, we did a little bit of damage to that, so let's keep going. We are going to move up. Now I need to deal with this negative pi over 2 that is being multiplied times y squared. So in order for me to move that to the other side, I'm going to multiply by the reciprocal of that expression, negative 2 over pi, on both sides of the equation. Okay, that will allow me to cancel this with this, and I will get negative 2 over pi multiplied times 100, x minus 100, and that is equals to y squared. Okay, we're almost there, not quite done. We need to deal with that square and the y, so I'm going to take the square root both sides of the equal sign, and in this case I'm not going to worry about the negative version. We discussed in class that we will have two solutions, positive and negative, since I'm only caring about values of x for which is greater than 0. I only care about values that are positive, so I won't have to deal with any negatives in this expression. The square root of y squared is going to be y, and This is just the same, negative 2 over pi times x minus 100. Okay, this new y that we solved for, this is what we call the inverse of x, and that is what I was asked to find. Therefore, I'm just going to box that, and that is our solution to this this problem here. Okay, so we found the domain and range in the context of this problem by just figuring out if it helps to draw it. Sometimes it does. To me, it does. And we found the inverse function. In this case, inverse of x, a inverse of x, which is the square root of negative 2 over pi times x minus 100. Okay, we're going to switch to the next part of the problem here. We're going to pick it up from here.